Hello, everyone. Welcome to our new webinar called Experiment QKD in Your Lab. My name is Catherine Simondi. I'm in charge of marketing and communication at ID Quantic. We have on the floor Tyle and Florian today. In this webinar, we'll be discussing QKD technology and also several lab setups consisting of QKD systems with external single photon detectors. Our speakers today are Florian Froes. Florian has a strong background in quantum physics, having earned a PhD from the University of Innsbruck in Austria. He furthered his expertise through 5 years of postdoc research at the University of Geneva, where he started collaborating with IDQ in the groups of applied physics. Florian joined IDQ in 2018 and has recently also joined the business development team of Quantum Safe Division at IDQ in Geneva. Tyle Stelzik is our product manager for quantum sensing. He received degrees in physics and maths from the University of Rochester in the US, and then completed some graduate work at the University of North Carolina. He is based in America. His current portfolio of products at IDQ is centered around superconducting nanowire single photon detectors, SPDs, and high-performance timing electronics. So again, thank you for everyone for joining this webinar. Please note that the questions will be taken at the end. You can put your questions in the Q&A bar. I can see that there's already one question, so don't hesitate. And there we go. Thank you very much.
Thanks, Catherine. Thanks, everybody, for joining. It's a great pleasure to talk to you today about applied research with QKD. So before jumping into the topic, let's start with the why we're all doing this. And in the end, it's to make the data of people, of organizations safe. And we know that the value of our digital data is increasing. We have more and more data stored digitally, far away potentially. And also fragility is increasing due to globalization, standardization, monocultural solutions. So it's very important to put more and more effort in keeping this data safe. At the same time, we know that technology is increasing the potential of risky technology like the quantum computer, which brings a lot of good things, but also can break current crypto systems. And this is at the horizon of a few years only. And there are other attacks like harvest now, decrypt later, where there's a lot of uncertainty about the risk and the impact. So it's undeniable that we have to act on this, that we have to make our data in rest and in transit quantum safe. And luckily, we have solution at hand, quantum key distribution, post-quantum cryptography, and it's on us to make these solutions valuable and useful for the organizations and the people. Just a word, why QKD? Why is post-quantum not sufficient? Again, about 2030, we expect a cryptographically relevant quantum computer appearing. And at this point, at the latest, you cannot trust on traditional asymmetric crypto anymore. The risk becomes too high. Post-quantum cryptography is supposed to be a quantum safe alternative. And for sure, this is there's good evidence that this is true, but on the short term, there's the risk of implementation errors that appear due to early releases. And in the long term, we know that since the foundations of post-quantum are less secure, it's not, there's always the risk that there is a fundamental issue with post-quantum cryptography. And therefore, for us, it's clear that quantum key distribution should be used whenever possible. And since a few years, we say that hybrid solutions composed of post-quantum cryptography and QKD is the best you can do to protect your data in transit. QKD is a technology that is relatively mature compared to other quantum technologies. But we all agree that there is a lot of work to be done for us in order to increase this value to cost ratio, for example, and increase the value for the end user in general. And there are many different aspects and levels where we can work on. starting on the fundamental level of the components that go into the system, like photon integrated circuits. We can still do a lot of QKD protocol research. And then on the other end, as an industry, we are working a lot on productization, commercialization, and scalable deployment methods. And in between, there are a lot of fields where we, so you as researchers, we as QKD industry can work together. And this is what we want to cover in this webinar. And this is about optimizing QKD performance, integrating QKD from an optical transport network point of view, but also from a cryptographic architecture point of view. And it's also about standardization and certification. So in the rest of this webinar, we are covering these aspects here. First, I'd like to give you a few technical and industrial trends that we see, and that we also, some aspects we're working on to give a bit of an idea what we are doing today at IDQ. And then we go more into the research direction. First, we will introduce to you the XGR platform, which is a QKD system that is industrialized but open to do research with. And then in the last part of the webinar, we will go into a few examples of how you can best use QKD in applied research. All right, so just to bring us on the same page, I assume that we have a lot of experts today in the webinar, but just to start with the basics. We have QKDs is a provably secure way of exchanging keys to two remote sites, Alice and Bob in the jargon. And the simplest use case is data center interconnect, where you have a data center and a backup, and you want to back up the data of one data center to the other. And for this, you use QKD to distribute the key. So you have two boxes, Alice and Bob again. They are connected via quantum channel and some auxiliary channels, and they implement and execute a QKD protocol. And at the end, they have a secret identical key on both sides. And this key locally they export to their to another cryptographic function, to another device, for example, encryptors.
And then the encryptors take this key on both sides and encrypt and decrypt the data in transit with this QKD key.
However, we have like three aspects three components that make the overall end-to-end key delivery quantum safe. The first element is a random number generator that is locally creating the user keys. So the secure application on the top left here is requesting key, and this is generated locally.
Then this locally generated consumer key is transported to the other side, to side D here, and then expected to be requested by the secure application. This transport is secured with QKD, and in case the distance limitation of QKD doesn't allow for direct point-to-point connection, we use trusted nodes to transport QKD keys here on the bottom. They receive the encrypted user key, decrypted and encrypted with the next QKD key before sending it to the next hub. So QKD is the second aspect. The third aspect is asymmetric crypto. It is used end-to-end between sites A and D to make sure that the user key is never in clear inside the trusted node. So it's only the endpoints that have the key in clear inside the nodes. We have asymmetric crypto that secures the user key, and today this is typically elliptic curve, and in future it's post-quantum.
This more or less defines implicitly or explicitly the network architecture. And IDQ is building complete QKD networks in this sense.
In general, we have many nodes. You have potentially many applications or many users, and therefore we have this glue in form of a network software which transports the locally generated user keys through the network, secured by QKD keys.
So on the lowest layer, you have the infrastructure, the QKD point-to-point links, and in the middle layer, you have the software that makes sure that the keys are well transported to the endpoints.
What we're doing at IDQ is also to extend this picture and this network architecture to situations where, for example, QKD cannot reach an edge node and is hence not covered by this QKD network. What is important here is that the user interacts with the same interface, that is locally with the same software module. This key management module takes care of the best and most secure way of transporting the key through the network as a function of the underlying infrastructure.
And today we are able to build rather complex QKD networks. So this is one important example that we like to highlight. It's in South Korea, governmental networks. It's a QKD network that spans basically the entire country of South Korea, and it's composed of roughly 27 QKD links. And here on the right-hand side, you see the schematics. It's all the three layers that I showed before overlaid, so it's a bit complex. But just to give you an idea that this is already a rather complex network that serves 48 governmental organizations in South Korea. And with, in the end, on the consumer, the secure application layer, we have more than 100 point-to-point connections. Another example is the network that we're currently building in Singapore together with Singtel. This is interesting because Singtel wants to offer QKD as a service to its customers. And here we are working a lot on business models and way of making QKD cost effective for the end user. And this is a very important aspect. If we want the QKD has a success in the end, we have to make offers that are cost effective for the enterprises and businesses. Let me finish this first part by having a quick look at standardization and certification. So for standardization, I take the example of ETSI.
This network architecture is now the dominant paradigm today for QKD networks, which is possible because of several standards that have been developed at ETSI. I can't go into any details, but these numbers refer to group specifications that were published by ETSI recently. And thanks to the work of this group, it's now possible to build QKD networks that are interoperable and where several vendors can come together to build the management layer, the key transport plane, and the infrastructure level of the QKD network. The other standards here, 018 and 020, allow to connect an orchestrator and to other key management systems respectively. The 014 interface allows to interface to encryptors, for example, and today there are about a dozen encryptor manufacturers who are compliant with this standard.
So there is a rich ecosystem building up currently. And certification is another important topic. It's needed to build trust for the end user, and it's needed to prepare accreditation for governmental use cases. And we are working on this. So we as the community, the QKD community, we have first documents published, for example, a so-called protection profile, which is a conceptual standard in concrete area. The other conceptual standard or basic standards are done at ISO. This is good. This is done. Some background documents are missing. We need to standardize evaluation methods, and we have to train labs. There, for example, in Europe, there is this new project Nostradamus working on this. So things are moving. However, there are also there are faster countries where things are done a bit in a more hands-on way. For example, in Korea, where they're working intensively on certifying QKD. And this is also a valuable approach. Also, not to forget standards or frameworks like FIPS that can cover non-QKD aspects of the entire product. So it's also very useful and something we're looking at. All right, so let's come to the QKD platform XGR from IDQ, which we offer as a research tool to do applied research with QKD.
IDQ has developed QKD since more than 20 years, as many of you probably know, and we currently have the 4th generation of QKD systems commercially available. This family, XG, has 2 members.
One is Cerberus XG. It's based on the COW protocol and has a dynamic range of up to 90 kilometers. And Clavis XG is based on BB84 protocol and has a dynamic range of up to 150 kilometers. In both XG products, they are highly industrialized. They are made for in production use and also from operational point of view with data centers, etc. So this is and inside, for example, in the Clavis XG, we have the QKD protocol implemented. And I assume that most of you are familiar with the basic concept of QKD protocols. I'm rushing a bit through this now, but obviously you can ask questions or we can talk about details later. But in principle, both sides, Alice and Bob, they have some processing units, FPGAs, microprocessor. They have a QRNG locally inside the box for their random choices needed for the QKD protocol. And in Clavis XG, we implemented the BB84 decoy protocol. It's a 4-state protocol encoded in the time bin basis.
Time bin means that each pulse is divided into 2 temporal bins called early and late. The basis that we use later for the key distillation is actually defined in this way. If the photon arrives early, it's a 0. If it arrives late, it's a 1. The complementary basis X is a superposition of early and late with well-defined phases 0 and pi. Inside of Alice, these pulses are prepared. After an unbalanced Mach-Center interferometer, there are an intensity modulator and a phase modulator, followed by filters and attenuators. On Bob's side, there is passive optics including another unbalanced Mach-Center interferometer and 3 single photon detectors to measure the state. Based on the XG product, we have the XGR variant, which is the same hardware and based on the same software stack, but gives you more access to and more control over the system than the production system. The first thing is that the user of the XGR has access to the raw data and intermediate data of the protocol. These are the raw key, the sifted key, the error corrected key, and the final key. But there are also parameters you can access. For example, you can switch on and switch off the QRNG. You can then, which I explain later, even impose a fixed preparation sequence. You can play with the decoy intensities. You can play with the probabilities of how frequently the bases are prepared. You can change the settings of the detectors on Bob's side, and there are, let's say, a dozen more parameters you can play with. And this is a new feature, which is only for Clavis XGR. You can plug in your own external detectors. This means that there's a small physical interface in the back of Bob where you can plug in your single photon detectors and reinsert the measured outcome back to Bob.
Right, so this is the XGR platform. It's the XG with additional research functionalities. And who should consider using this platform? This is meant for people and researchers who have research questions based on industrialized or mature QKD systems. If you want to know how mature QKD systems integrate into your bigger setup, this is surely an option to consider. It's also for people who don't want to lose a lot of time with building up their own setup. So you have access to the full net software stack from the IDQ XG product. And it's also a turnkey solution. It's a quick start for you. It's not so much for researchers working on basic quantum optics or doing fundamental research on QKD protocols. And why should you add external detectors? Because they're already built-in detectors that come with the system. It's first of all, you have more control typically with the external detectors. You have also more insight because you can monitor what's happening with each individual detector. And for some detectors, you can expect a better performance. And Ty will talk about this later. All right, so let's have a quick look in different research directions to see what you can do with this platform. So the first direction is not, let's say, direct research, and it's maybe almost a bit trivial for people who who do very detailed QKD research.
But it's still very important for the entire community to train, to teach, and to create awareness about QKD. The XGR is a nice platform to demonstrate how QKD works to local governments, to authorities. It's great to train technical staff, and it's certainly an interesting research tool for teaching at applied universities. What I said before basically applies directly to what you can do for this purpose. For example, you can add optical elements on your quantum channel to simulate noise or simulate an attack, and then you can look at the raw data and intermediate data to see the impact of this on the performance of the QKD system and its behavior in general. Also, you can change different parameters as said, so combining this with the optical elements allow you to see the impact. And if you add external detectors, you may want to collect the clicking events with a time-taking electronics. With this, you can even collect more statistics and get more insight to see what's happening inside the system and how the QKD protocol is executed. The second research strain goes in the same direction as before from the methods point of view. But now we are interested to do more systematic validation of the protocol by collecting evidence that what the manufacturer, in this case IDQ, promised to have implemented is indeed correctly implemented and executed.
This is a kind of gray box testing that you can do with this system because you have access to some parameters and you can see what's happening during the execution of the protocol. And this might help you to contribute developing standards, for example, for test methods. And again, the methods are similar to what I said before, so I don't repeat this, but generally you can do all this in a much more rigorous way. You can do statistical analysis and compare the theory and the model with the sampled raw data, for example, that you collect from the system. You can also check how the QRNG inside these boxes work. And an interesting example here is the group specification 012 from ETSI, which is a method how to test the optical output on Alice side to see whether what is, again, promised by the manufacturer is indeed implemented. And for this, you then can use this input, this given sequence of pulse preparations. This means you have a pen drive with, I don't know, 1,000 preparations, and this is inserted into Alice, and then Alice in a loop creates these pulses based on your sequence, and then on Bob's side this is obviously measured, and with external detectors in particular you can then verify that the pulse sequence that was given by you, this pseudo-random number sequence, is indeed well implemented. Okay, with this we come to the third aspect, and here I'd like to hand over to Tal. So let me give the control to Tal. I hope this works.
Great. Let's hope so. So yeah, thanks, Florian. I appreciate it. So as mentioned, the Clavis XGR can be used with external detectors to replace its internal single photon detectors. This gives a lot of flexibility, and I'll be discussing a few ways in which this opens up research directions related to improved QKD performance in industrialized systems, both via SPADs that are better attuned to a particular experimental setup, and especially using high-end detectors like SNSPDs for better performance. There we go. The first level of this, I'll talk about 3 levels of roughly increasing complexity and performance together. So the first is optimization of SPAD-based external detectors for different deployment scenarios. IDQ offers several in-gas SPADs optimized for telecom wavelengths. First, we have our ID Cube series. operating in the near IR and optimized for 1550. The ID cube can achieve 10 to 35% quantum efficiency at 1550 with around 500 counts per second of dart count rate at 10% quantum efficiency. And all of this in a compact form factor. It's approximately 10 centimeters on each side of that cube. We also have the ID 230, which has better noise performance than the cube, quite unique for a SPAD, really, but with higher afterpulsing probability to manage and slightly lower maximum efficiency. And it's also on the order of 30 kilograms rather than 1 kilogram. But all of IDQ's near IR single photon detectors, are designed to be compatible with the Clavis XGR. But now, why would you want to do this? After all, the Clavis already has SPADs inside of it. The reason is that external detectors will offer more control and more accessible parameters of the single photon detector. So for example, here we can see the GUI for the ID cube. And as you can see, there are a number of user adjustable parameters, the efficiency, the dead time being especially relevant here. So, for example, regarding the efficiency, you can adjust this between 10 and 35% in 5% increments based on just the voltage across the diode. There's a trade-off between efficiency, dart count rate, and jitter, such that at higher quantum efficiencies, the detector will have higher dart count rates, although also a lower jitter. And so you can see a schematic showing this relationship on the right of the slide. As I mentioned, the dead time can also be adjusted between 100 nanoseconds and 80 microseconds. And together, these parameters give you a space to explore in terms of tuning your detectors to your particular application. Now, we can also combine the Clavis XGR with superconducting nanowire single photon detectors for the best performance. You may have heard the good news about SNSPDs, so to speak. These are truly the best in single photon detection. With incredibly high detection efficiency, low dart count rates, unparalleled timing precision, and fast recovery times. I won't go through the details of our products, but I'll just say that we've been developing and producing SNSPDs at IDQ for about 8 years now. It's amazing to see both the performance improvements our R&D team has achieved over that time to detector performance, as well as how much simpler the product has gotten for the end user. We offer 2 fully integrated SNSPD systems, each with up to 16 detector channels. That's first the ID281, designed for a lab context, and now the ID281 Pro, an intuitive rack mountable system designed for reliability and ease of use. So let me show a bit about the performance that we might expect. So at IDQ, we have developed let me take a step back. So as many of you, standard SNSPDs based on a linear meander are polarization dependent. So the detection efficiency is a function of the polarization of the incoming light. So the quantum efficiency might vary by approximately a factor of 2, say between 45 and 90%, depending on the polarization of the incoming light relative to the meander of the detector. And so I'll talk about 2 solutions to this. And so first, at IDQ, we've developed polarization insensitive SNSPDs, specifically optimized for QKD performance with the Clavis XGR. And I will show the relationship between the secret key rate and the attenuation that we can achieve with this setup. So this data was taken with the Clavis XGR and our polarization insensitive SNSPDs. So you can see something like 400 kilobits per second secret key rate at 12 dB. That's typical performance. And at least 40 dB dynamic range can be achieved as well. So that was with these polarization insensitive detectors, which do, however, have slightly lower performance or quantum efficiency compared to a standard linear meander. And so an alternative to using the polarization insensitive SNSPDs is using standard SNSPDs with either external polarization control or using 2 detectors per mode. And so I'll show just a simple schematic of a way in which this could be done using a polarizing beam splitter for each channel. The idea is simply that you tune the polarization of each input is tuned to the maximum detection efficiency for the SNSPD in the corresponding channel. And this setup gives better performance at the cost of somewhat greater system complexity. So if you're really trying to push it to say, 50 dBs or beyond, that this would be the way to go. So now, as I had mentioned before, IDQ's SNSPD systems have 16 detector channels in each cryostat. So a single ID281 or ID281 Pro system can serve up to 5 Clavis XGR receiver modules in parallel, allowing, for example, as shown here, to build a star topology with 5 links over, say typically shown here around 200 kilometers. The central node in this example, using the ID281 Pro, is only 23 U high, and that includes the compressor and vacuum pump, which are part of the system but not shown here. So I think this really opens up a lot of exciting options. So I'll end it there. So thanks. And with that, Florian, I will hand it back to you.
Thank you, Tal, and take back control. Yeah. I was informed that there was a bit of a connectivity issue, that my voice was not hearing very well. So we changed on the fly now the system, and I hope it's working better now. So let's come back. Let's go on with the different research directions that can take advantage of the XGR platform. And the fourth example I'd like to give is integration of optical transport networks. It's true that with commercially available and fibers that are deployed today worldwide, it's no issue to use QKD to carry the quantum signal. However, multiplexing the quantum channel with third-party intensities, classical intensities, is non-trivial. And in particular, systematic research on this topic, taking different external factors into account, is something that is really needed to make this more a better technical solution in practice. And there has been a lot of work already done in the past. So I'm citing one paper here from the University of University of Geneva Group of Applied Physics a few years ago. And what you do typically when you multiplex a DV-QKD system like BB84, what we have, is that you put the quantum channel on 1310 nanometers, and multiplex this with third-party channels in the C-band, around 1550 nanometers. And then, so you have the multiplexing here, and then different factors impact the QKD performance. So the length of the fiber, the attenuation of the fiber segments, and also obviously the intensity of the third-party channels and the wavelengths. So it's really on the impact of this Raman scattering that adds more noise to the QKD channel that is researched here. And if you do this with the XGR platform, then you can play with the external detectors or the internal detector settings to optimize the QKD performance. You might add additional filters on the optical modes to better cope with the random scattering. All right, with this, I'd like to come to the last example I'd like to give. It's a bit different in the sense that it's not so much on the optics, but more on the cryptographic aspect of QKD and how to make hybridization solutions based on QKD. So we acknowledge that in different use cases, different combinations of cryptographic primitives from mathematic crypto and QKD, the best solutions. And it's also this aspect is important to overcome a bit these technical and cultural gaps we historically have between the communities of cryptographers and physicists. And this is, from this point of view, also very important. And I just want to give you two examples. The first one is from Doling and co-workers a few years ago, and they worked on hybrid authenticated key exchange methods. This was the QR code here leads you to the preprint publication, and they show how to use QKD and other sources together to have the best key exchange method in a hybrid mode. And the second example I'd like to highlight is what we've done recently at IDQ. It's also part of the product now. It's an additional method or mechanism, to transport the secure consumer keys. So again, as I explained in the beginning, typically you have locally a QRNG that generates consumer keys, and the consumer keys are transported to the other side using a key from the QKD link. And then typically you have one-time pad to encrypt the user key, which is called KQRNG here, by the QKD key, KQKD. However, you can also use one QKD key to encrypt several consumer keys by using symmetric encryption. So with this, you lose the ITS, of the key delivery. So it's no longer information theoretic secure, but it stays quantum safe. And at the same time, you gain a lot of performance because then you can encrypt a multitude of user keys with one single QKD key. And in a point-to-point connectivity, this is typically not necessary, but in very complex networks, QKD networks, this could be an issue. Or if you go later to satellites, this is also an interesting method. And therefore, when configuring the consumer paths in the QKD network of IDQ, then you can choose one or the other and also set the refresh rate in case you choose AES. Okay, with this, I would like to conclude this webinar. I think it's clear for everybody that we need more research and more collaboration in different disciplines where QKD is concerned. IDQ offer this open-QKD platform XGR, which we think is a good platform for applied research with QKD. On the bottom, you see a table where we suggest different combinations of XGR, Clavis XGR, and external detectors for the use cases for the different research directions that we presented in this webinar. So the simple and obvious but still important message is: let's work together. Together we can make QKD a success. So with this, we're done, and I think we can go now to the questions, right, Tyler?
Yeah, let's so yeah, we've got a lot of questions. We will not have time to answer all of them in the webinar, but we will reach out over email with answers to the ones that we don't get to. So here's one from Leon Brown. is it correct that to achieve reasonable distance, you must implement and trust IDQ's Clarion KX? For example, in the Korean and Singapore contexts, who manages the trusted nodes and their security?
Well, this is a quite complex question, to be honest. I mean, there are different levels of answers I can give to this. So from a very, let's say, physical point of view, trusted nodes are necessary whenever you go beyond a certain distance, typically, let's say 100 kilometers, depending on the quality of fiber and the details of the implementation. Let's forget about satellite QKD for a moment. Let's only focus on fiber-based QKD. If you want to go beyond this, then you need trusted nodes in between. There is no way around. It doesn't. So our solution is not really related to this. It's like a physical constraint. And then what we propose as a complete solution is this software and hardware package that with this you can build up your end-to-end key delivery. But it's not necessary from a fundamental point of view to use our Clarion KX, which is the software that does this job. Thanks to the standards that are available, this is interoperable. So IDQ offers the full solution, so QKD, hardware and software to do the network, but it's interoperable with other vendors.
Great, thank you. Let's see, there were a couple of questions that I'll just hit very briefly around the detectors. Somebody asked, are the ID cubes in the near IR polarization dependent, or just the SNSPD? Just the SNSPD, yeah, the SPAD detectors are not polarization dependent. Somebody also asked about the lowest possible gate time from the cube. And so we do make both a free running and a gated version of the cube. For the gated version, the gate times are on the order of a few nanoseconds with repetitions of up to 100 megahertz. Let's see, so could you say, so from Jefferson Flores, he says, by sample raw data from the QKD protocol, do you mean preparation and measurement bases and states? So could you say a little bit more about the raw data?
Sorry, can you repeat the question?
Yeah, the question from Jefferson was, by sampling raw data from the QKD protocol, do you mean preparation and measurement bases and states?
Yeah, so this is, sorry, I tried to jump to this slide. It's really, there are different levels, right? The raw key contains the basic preparation measurement information. So exactly what has Alice chosen to prepare in terms of these four states, set 0, set 1, x0, x1, and what has Bob measured, really in the level of physical clicks. And then if you go to the next level, sifted key, you get rid of events where Bob didn't detect anything, and then you go to error-corrected keys, where Alice and Bob should have the same information, and so on. So you can go down really to the physical level by looking at the raw key.
Great. And then so many to choose from, but let's do one last question. And there were a few people asking questions in this area. So let's end with something slightly big picture. So for example, Francisco Javier de la Puente Sequedes asks, why should we use QKD instead of quantum encryption algorithms proposed by NIST?
Well, I mean, this is a tough one in the sense that it's all about future, and future is unpredictable, as we know. And who knows, who can tell physically, who can quantify the risk of PQC failure in 5 years, in 10 years, in 15 years. This is, I mean, from a scientific point of view, it's unreasonable to try to find the number. For sure, we agree that the number might be small, but also the impact is huge. And the first thing I learned in university when doing physics is never multiply a very small number with a very large number, because the product has an error bar that is order of magnitudes beyond the value. So for me, this boils down into even a political decision, to be honest. I mean, it's personally, I find it unreasonable not to consider QKD, given the threat and the risk potential. On the other side, it's scientifically, it's difficult to prove.
Great. Yeah, thank you very much. We have about 40 questions we didn't get to, many quite technical. So we will reach out to answer questions for anybody who had submitted them. But let's based on the time, let's end it there.
Yeah. So maybe if you could stay one more minute, we'd like to launch a small poll. It's just for us as a feedback, how you like the webinar, and yeah, if you want to have more contact with us later. And it's just 2 yes and no questions, so it should be easy to answer and fast. But in the meantime, I'd like to thank you for your attention. It was a great pleasure to talk to you on this topic. It's very rich, and yeah, hope that we have another chance soon to meet somewhere else on this. And I'd like to thank also Catherine and Tal, who helped me and made this webinar a nice experience, I hope, for you. All right. So I think again, thank you a lot, and we can close the webinar. Thank you. Bye-bye.
Yeah, thanks, everybody.